In this module, we're going to take another look at the dynamic allocator, specifically everything that happens outside of TCACHE. Now, we've spent a decent amount of time talking about TCACHE and how it works. We've said that TCACHE consists of a number of fixed size bins. And these bins accommodate chunks up to a size of about 1032 bytes. Each of these bins can hold up to 7 chunks of its specific size. And these chunks are stored in a singly linked list. These singly linked list next pointers are protected via a mechanism referred to as safe linking. And safe linking uses XOR with some random bytes to obscure the next pointer from an attacker. When talking about the TCACHE chunk metadata, we saw a struct that looked similar to this when the chunk was free. It consisted of a number of values: a previous size, the current chunk size. Note that the least significant bits of the size value have 3 flag values, A, M, and P. A indicates whether or not the chunk was allocated from outside of the main arena. M indicates whether or not the chunk was M-mapped. This would occur for very large allocations where kind of the standard heap mechanisms don't make sense. P indicates whether or not the previous chunk is currently free or in use. It is referred to as the previous in-use flag. Now, when we were doing TCACHE exploitation, the primary metadata values that we messed around with were the next 2. The next pointer, which is located at the address of the allocation, and the key value. Now, the key value itself was not very useful. However, when safe linking is not enabled, this key value is a pointer to the TCACHE per thread struct, and that has some implications. However, on a modern libc, we have the key value, which is just some randomized bytes, and that doesn't provide an attacker with very much information. So what we primarily interacted with was this obscured next pointer. So we've said that the TCACHE uses a singly linked list to manage free chunks. And it does this via 2 arrays. An array of counts, which is just an integer for how many entries are in a particular bin size, and an array of head pointers. And these head pointers point to the allocation address of the free chunk. At the allocation address of a free chunk is a next pointer. And that next pointer points to the allocation address of the previously freed chunk of that bin size. Now, the TCACHE per thread struct only accommodates a certain number of bin sizes. Similarly, the list for a particular bin size has a maximum size. For TCACHE, each of these lists can only be up to 7 chunks in length. So what happens when I free an 8th chunk? What is the heap going to do? Well, it's going to follow this flow chart here. And so if we can put it in TCACHE, we put it in TCACHE. If it can't go in TCACHE, it's going to go into something called fast bins. And we'll talk about fast bins in greater detail in the next lecture. If it can't go into fast bins, then the dynamic allocator is going to check and see if the M bit is set. Remember, the M bit is a flag value in the chunk's size least significant bits. If the M bit is set, then the allocation was created via mmap. And so to clean this up, it would call M unmap. Now, if it's something that is not able to go into TCACHE and it's not able to go into this fast bins, then it's going to end up in this unsorted bin. Now, the unsorted bin is exactly what it sounds like. It is just an unsorted list where all chunks go if they don't fit into TCACHE or fast bins. The only other thing worth noting here in this flowchart is that if the freed chunk is exceptionally large, in this case larger than 65 kilobytes, then the dynamic allocator will do some cleanup and maintenance where it's going to clear and consolidate the fast bins. Again, we'll explore fast bins in greater detail in the next lecture, but it's worth mentioning on this slide so that you have a complete picture. So what about malloc? Well, malloc follows a very similar order of operations here. except instead of trying to put the chunk into one of these bins, it's going to try and retrieve them. And since we're trying to retrieve something, we may end up having to do some sorting or figuring stuff out. So let's follow this flowchart here. Well, first, if we malloc, can we get it from the TCACHE? If we can, that's great, we got it. But if we can't get it from the TCACHE, then we're going to check this thing called fast bins. If it can't come from fast bins and it's small, then we're going to look in the small bins category. Small bins will be discussed in greater detail in the next lecture. But what if it's too big for small bins? It can't go in TCACHE, we can't find what we want in TCACHE, we can't find what we want in fast bins, and it's too big to possibly be in the small bins. Well, if that's the case, then we're going to clean up fast bins, and then we're going to start going through that unsorted bin pile, right? Remember, the unsorted bin is what happened here when we freed. Everything that couldn't be cached in TCACHE or fast bins went into this unsorted bin. Now, when we malloc, if it's larger than the small bins can handle, then we start going through the unsorted bin. And we look at the chunks that are in there, and if the chunk that we are looking at is large enough to satisfy this malloc requirement, then that's what we'll return. If the chunk is not large enough to satisfy the malloc requirement as we're going through them, then we will sort it, which means that we will place it in either the small bins or the large bins based upon its size. Now, if we've gone through all of the unsorted chunks and we still haven't been able to satisfy this malloc requirement, then it must be something large that they're asking for. And so we'll take a look at the large bins. And the large bins, as the name kind of indicates here, holds large chunks. But what if there haven't been any large chunks and we can't find something large enough for this request in the large bins? Well, if it's exceptionally large, then the allocator will call mmap, right? And set that m bit. But this is for like exceptionally large requests. If it's just large and we haven't made large chunks yet, right? And so like the large bins haven't been filled, we haven't started putting stuff in there because we're early in a process's lifetime, then we're going to create the chunk from the wilderness. And remember, the wilderness is kind of this giant chunk that consists of everything in the heap that hasn't been turned into a chunk. There's just like this giant chunk that is everything that isn't a chunk, and we refer to that as the wilderness. So there's a lot more mechanisms going on once we look past TCACHE. In addition to all of these additional bins, there's more metadata in the freed chunks. We see here that in freed chunks that are not in TCACHE, we still have a previous size. We still have a size. We still have the A, M, and P flag values in the least significant bits of the size. But instead of having a next pointer and a key, we now have a forward pointer and a backward pointer. And in the case of large freed chunks, we also have a forward next size and a backward next size. So in a single freed chunk, there could be up to 4 pointers that navigate all of these chunks in different ways. So why do we need all of these additional pointers? Well, we need these pointers because there's more lists. So TCACHE is a singly linked list. FastBins is also a singly linked list. So FastBins is going to work pretty similar to TCACHE when we talk about it. However, for unsorted bin, small bins, and large bins, these are doubly linked lists. And so the forward and backward pointer are going to be involved for any freed chunks that are in these 3 bins. So let's take a look at what the doubly linked list kind of looks like. So a doubly linked list means that we have a forward pointer and a backward pointer. Now, it's going to still be similar to TCACHE or kind of our singly linked list mechanism in the sense that for the small bins, for example, there is going to be a head pointer. That's the entry point into the list. And that head pointer is going to point to one of the chunks. The difference is every one of these chunks can be navigated in one direction via the forward pointer until it loops back around to chunk 1, or they can be navigated in the reverse order by repeatedly calling the back pointer until it loops back around. And so you see how both of these lists are cyclic. Whether I navigate the forward direction or the backwards direction, I can come back to chunk 1. And so the head pointer is not really directional. It simply points to a chunk. So why use a doubly linked list instead of a singly linked list like what we've seen with TCACHE? Well, the answer is a doubly linked list allows for a lot more efficient removal of items because we don't have to traverse the entire list to update it. And the reason that we're going to be updating or removing items from these lists on a more frequent basis than we do with TCACHE is because of something that's known as consolidation. Consolidation occurs when two neighboring chunks, and when I say neighboring chunks, I mean two chunks that are right next to each other in virtual memory, are merged to create one larger chunk. Now, this consolidation step can occur when a chunk is freed, and that makes some sense. I've freed a chunk, we're passing it into the heap. The neighbor may be free, we merge them together into one. But it can also occur when a chunk is mallocked. And at face value, it doesn't make sense why calling malloc would cause consolidation to occur. Because when a program calls malloc, it's requesting a chunk. But based upon kind of some of the internal mechanisms of the heap and how some of these caching layers and bins work, the act of calling malloc can cause the heap to consolidate chunks that it is tracking internally. And this act of consolidation requires the removal of chunk entries from these bin lists when that merging occurs. So what does this look like physically in memory? Not in the lists, but in memory. Well, consolidation can occur both in the forward and backward direction. And in order for it to occur, the P bit must be cleared for a chunk to consolidate. If you'll recall, the P bit indicates that the prior chunk is in use. So right here, we have chunk 1 and chunk 2 right next to each other, contiguous in memory. Chunk 2's P bit indicates that chunk 1 is allocated. Chunk 1's P bit indicates that the chunk before chunk 1 is allocated. Now, how does chunk 2 know where chunk 1 is? It's not from the forward and backward pointer. These forward and backward pointers have to do with tracking chunks in lists or bins. As far as identifying chunks, as far as where they are in memory, contiguously, chunk 2 would look at its previous size to calculate where is the prior chunk in memory. So remember, there's a difference between moving through memory contiguously for merging and updating the forward and backward pointers of the lists. So let's take this as an example here. I have 3 chunks as an initial state, chunk 1, 2, and 3. All 3 of these chunks are allocated. Now, chunk 3 has its P bit set because chunk 2 is allocated. Chunk 2 has its P bit set because chunk 1 is allocated. Chunk 1 has its P bit set because I don't have it in this example, but there would be some chunk 0 behind chunk 1, which is currently allocated. Well, what happens when we call free on chunk 1? Well, chunk 1 is freed. This means that it's going to get inserted into some list or bin. It doesn't matter what bin it is. And when that occurs, the chunk 1 is going to get a forward pointer written and a backward pointer written. It may get 2 additional pointers after that if it is a large bin chunk, but we'll cover that a little bit later. One thing that will occur, though, is the forward and backward pointer will get added as metadata because it's a free chunk. Now, chunk 2, we see that there were some changes there as well, even though what we freed was chunk 1. By freeing chunk 1, we are updating the metadata in chunk 2. Chunk 2 now has a previous size value, where before it wasn't necessarily going to be there. We see that the previous size for chunk 2 is updated to hex 120. We also see that the P bit is cleared from chunk 2's size. So it would have been hex 101 because the P bit would be set. And by clearing that, it becomes hex 100. But the actual size of chunk 2 is hex 100. The least significant bits there are just tracking the A, M, and P flags. So far, nothing fancy has really occurred. We've just updated some metadata. But what happens if we were to free the allocation that corresponds to chunk 2? Well, when we free chunk 2, we would need to update the metadata of chunk 2 with the forward and backward pointer. We would then clear the prior in use bit that is in chunk 3, which we see occurs, and then the previous size for chunk 3 gets updated to show the size of chunk 2. But what happens if these two chunks, chunk 1 and chunk 2, get consolidated? Well, the act of consolidation combines these chunks into one larger chunk. Now, chunk 2, when it's freed, can know that it's a candidate for consolidation. And it knows it's a candidate for consolidation because chunk 2's previous in-use bit is not set. Because chunk 2's previous in-use bit is not set, it knows that the chunk behind it in memory is also free. So it makes sense to combine these two chunks into one larger allocation. And we can see that happen right here. We see that the size of chunk 1 gets updated to be the size of chunk 1 plus the size of chunk 2. We also see that chunk 3's previous in-use bit is still clear because the combined chunk after consolidation is still free. But what does change is chunk 3's previous size. Chunk 3's previous size was hex 100. And that was correct because that's the size of chunk 2. But when consolidation occurs, the next immediate chunk behind chunk 3 is now chunk 1, and it's a larger chunk 1. So the previous size of chunk 3 gets updated to hex 220. So that's great and all, and that's what occurs in physical memory. Because remember, this is in physical memory, so we're in a contiguous memory region here, from hex A010 to hex A650 in this example. But what about these lists? That still doesn't explain why we need a doubly linked list. Well, in our example here, what we freed was chunk 2. And by doing that, chunk 2 disappeared because it consolidated with chunk 1. So if I have a list in any of these bins here that is tracking chunks, chunk 2 used to be in this list, but when consolidation occurs, we need to remove chunk 2 from the list. Now, I know where chunk 2 is, but I don't necessarily know what list it's in because I don't know the state of the heap. So is there a way that I can update the list that chunk 2 is in without having to traverse all of these lists and try and figure out where is chunk 2? The answer is yes, and that's why we have this doubly linked list. No matter what list chunk 2 is in, we can take the forward-backward pointer and set it to chunk 2's backward pointer. And we can take chunk 2's backward-forward pointer and set it to chunk 2's forward pointer. And this will remove chunk 2 from whatever list it is in, regardless of where it is. And this is why having a doubly linked list allows for very rapid removal of chunks from the list. Now, that was a little bit of a mouthful, but the end result is we can remove chunk 2 while only looking at the pointers that exist in the metadata of chunk 2. And so it doesn't matter whether this was a large bin, a small bin, an unsorted bin. We don't have to worry about that. As long as we follow the unlinking algorithm, we'll be removing the chunk from whatever list it happens to be in. Now, what does this unlinking look like in code? Well, this is the beginning of the unlink chunk function in libc. You can click the link in the slide here if you want to take a deeper look at it. Now, what we see here is that when a chunk is unlinked, so we're trying to unlink chunk P. Well, we save the forward value of the chunk we're unlinking. We save the backward value of the chunk that we're unlinking. Then, to perform the removal or the unlinking, we do exactly what I had just described. The forward-backward pointer, which is the chunk that is next in the list, its previous entry is going to be whatever is previous to us, to the chunk that's being unlinked. Similarly, the backwards-forwards pointer, so the next entry of whatever is behind us in the list, gets set to whatever is in front of us in the list. And we don't have to worry about what list we're in. And this provides very rapid and efficient removal of chunks from these bin lists. Now, we'll take a deeper look at this a little bit later, but it's definitely worth mentioning right now that we see there are checks here to make sure that these values are correct. We take a quick look at this first check up here. There is a check that ensures the chunk size of the chunk that is being removed or unlinked, which is P. If this does not equal the previous size of the next chunk, then there's a problem. We've corrupted the size. And that makes some sense, right? The size of the current chunk should equal the previous size of the next chunk in contiguous memory. Now, there's another check down here. And this check says the backward entry of the next chunk in the list should equal the current chunk. And the forward entry of the prior chunk in a list should equal the current chunk. And all this is doing is jumping forward and back and making sure we end up in the same spot. And then jumping backwards and forwards on these pointers and making sure we end up in the same spot. So for a correctly functioning heap, these are assumed correct. But in an exploitation scenario where these values may be manipulated, these checks will be the cause of a lot of problems and error messages. Definitely worth mentioning now because you'll be seeing these error messages as we move forward in the module.